Good morning, friends. Yesterday, we have completed analysis on 1D two-noded bar element, and it was called as a linear element because the shape functions what we had used, they were linear in nature, and there were only two nodes, end nodes, 1 and node 2. And we had used the two shape functions, namely n1 equal to 1 minus zeta by 2 and n2 equal to 1 plus zeta by 2. There are no any higher order terms, they are linear in nature because as the zeta varies, the shape function varies. The speciality of this, what we found out was the shape functions were linearly varying. That was n1 was 1 at node 1 and n1 was 0 at node 2. Similarly, if you take the shape function, other shape function n2, it was 1, n2 was 1 at node 2 and n2 was 0 at node 1. This was the linear variation what we found out. See, this was the linear variation for this and this was the linear variation for this. We have found out that. And we also found that because of this, the stress was expressed as E into epsilon, which is called as E into, you can say, B strain displacement matrix into Q. And we have seen that E upon LE minus 1, 1 and into Q1 and Q2. This being a totally a linear equation, and if you look at this, totally all these are containing constants. So therefore, what is the important observation? We found out that the strain and the stress, they remain at constant throughout the element for 1D bar element. That is 1D two-noded bar element. Now, if I want to improve the results, suppose if I want to increase the accuracy of the results, we have a provision to add more number of nodes onto our element. See, today we are discussing what is called as quadratic shape functions. When the shape functions are added with one more term, that is always you remember the order of the polynomial what is being used is actually the order of the element, you can say. Therefore, this here we are generating the shape functions in terms of quadratic terms. So therefore, we need to add some more nodes. So in the present figure, what I am telling you, it is called a three-noded 1D bar element. That means we are introducing another node that is called as a mid node. That is, we are adding n nodes are 1 and 2, they will remain as it is. We are introducing one more mid node 3 at the midpoint of that. See, this is the figure shown in x coordinate, that is Cartesian coordinates, and this is shown in the natural coordinates, that is zeta. So if you look at this, we can see there here, definitely you can see there here, node 1 is at x1, node 2 is at x2, node 3 is at x3, and x is the general term where we can find out the displacements or whatever it is. See, similarly, if you map that, we know that the value of the natural coordinate, that zeta, varies from minus 1 to plus 1, and since it is the mid node, the value of zeta is going to be 0 here. So therefore, there is going to be what is called as a mapping. We need to find out the mapping for this. See, the midpoint is introduced. See, midpoint node, that is node 3, is introduced for the purpose of passing a quadratic fit. We are passing a quadratic fit, we call it. And that is why, and this node is called internal node. The node 3 is also called as internal node. Please look at the sequence. It is not 1, 2, 3. It is 1, 3, 2. The name of the, you can say, nodes are given in such a manner that first one will remain as it is, the end will remain as 2, and midpoint is taken 3. Because this is going to be very much mattering when we are calculating the global stiffness matrix as well as the stresses. Which nodal displacements or how to assemble the global stiffness matrix and all that, it definitely matters as far as these local node number is concerned. These are the three local node numbers which are considered here. Now, for mapping, the zeta is mapped with x minus x3 upon x2 minus x1. This is the general formula for a given x. What is the corresponding value of zeta? So suppose let us test it. See, for example, we know that for x equal to x1, when I put it here, what will happen? Zeta will become 2 times x1 minus x3 upon x2 minus x1. Okay. So therefore, if you look at this, it will be, I can write it as, since x3 is greater than x1, I will take minus sign and I will write it as x1 minus upon 2 upon x2 minus x1. See, x3 minus x1, when you say here, this is going to be the x3 minus x1, that is this one. See, this part is nothing but, we call it as x3 minus x1, it is. And which is going to be definitely half of this x1 minus x2 by 2. So therefore, I will substitute this as minus 2 x2 minus x1 upon 2. And already it is x2 minus x1 is already there. So this cancels, this is cancelled. So automatically it is proved that the value of zeta is going to be minus 1 for the node 1 when x is equal to x1. Similarly, you can try for x equal to x2, you can try. What will happen? If you take zeta equal to 2 times x2 minus x3 upon x2 minus x1. Again, you know that this is also going to be equal to minus x2 upon x1 upon half into x2 minus x1. So once again this will go, the value of zeta at node, you can say 2 is going to be zeta is equal to plus 1, which we are confirming from this 2. This is already confirmed. And similarly, if I want to put x equal to x3, for example, if I put x equal to x3, what will happen? Zeta will be equal to 2 times x3 minus x3, which is obviously 0. So there is no need of going further. So, but still, this is going to be 0. So therefore, we are proving that the values of the natural coordinate zeta varies from minus 1 to plus 1. That is, whenever we want to integrate, always we vary if the length of the element is covered between minus 1 to plus 1. Now let us define the quadratic shape functions, because we have seen in the linear for these things we have seen. Now let us write quadratic shape functions. And always remember the number of shape functions like n1, n2, n3, n4 up to ni, if you are taking, it totally depends upon the number of nodes. If suppose if it is a 2-noded bar element, then I will be having only 2 shape functions, n1 and n2. But in this presently, in this case, as I am having 3 nodes, I will be having 3 shape functions. The first one, n1, which is a function of zeta, can be written as minus zeta into 1 minus zeta upon 2. And if I want n2, it is equal to zeta into bracket 1 plus zeta upon 2. And if I want n3, which is going to be 1 minus zeta into 1 plus zeta, or you can even write it as 1 minus zeta square. So if you look at all the 3 shape functions, we can find out that there is going to be one term, zeta square is involved, and we are already knowing that zeta square represents the quadratic fit, what you can say. The variation of the shape function is not linear, it is going to be quadratic in nature. So now let us see how exactly we are going to see this. See, let us say properties of what you can say shape functions. If I say it is ni, see, always the basic property of this ni is always given as 1 at node I. Wherever you consider, it is node I. And it is always going to be 0 at all other nodes. This is the property of all the shape functions. It is always unity at the given node considered. If you want n1 is always 1 at node 1. And it is 0 at 2, 3, 4, 5. Depends upon how many number of nodes are there. At all other nodes, it is going to be 0. So let us check this. How these 3 shape functions have been obtained. Let us check this. So first we will take, as I told you, N1 is going to be 1 at node 1, where zeta is equal to -1. Okay. Similarly, N1 is 0 at nodes 2 and 3, where zeta is +1 and zeta is 0. So that means whenever I put the value of zeta equal to +1 or whenever I put zeta equal to 0, my N1 must become 0. So therefore, this indirectly defines that N1 is in the form of zeta into bracket 1 minus zeta, because the moment you put zeta equal to +1, this whole thing will become 0. Whenever you put zeta equal to 0, this will become 1. Why I found out this constant C is, it has to satisfy this condition also. That means N1 is going to be 1 at -1. When I put zeta equal to -1, it should satisfy. That is minus of -1. When I put this one, this will be nothing but the 2C, or C is equal to half. This is what I am going to get. That is -half. I am going to get this as -half. This I will get -half. So therefore, our shape function N1 is of the form minus zeta into bracket 1 minus zeta upon 2. This is going to be the final shape function for the node 1, we can say. Similarly, let us take for node 2. For node 2, tell me what is the condition? N2 is equal to 1 at node 2. And that is node 2, what is the value? Zeta is equal to +1. And it is equal to 0 at nodes 1. That is zeta equal to -1. And it is equal to at node 3, we can say, where zeta is equal to 0. This is what we need to find out. So therefore, that means if I put again in the same form, that is, if I take zeta and if I put zeta equal to -1 or zeta equal to 0, the value of N2 should become 0. And other important condition is, if I put zeta equal to +1, I should get 1. That means 1 equal to C, and this is 1, 1 plus 1, which is equal to C by 2 it is. So therefore, rather 2C, this is 2C. So says C equal to +half, it is going to be +half for the shape functions like that. So obviously, if I want to find out N2 of zeta, it is going to be zeta 1 plus zeta upon 2. This is what we are going to get for the shape function N2. In the similar way, you can now plan for N3 also. We can plan it here. See, for example, here, let us see N3 at node 3. At node 3, the N3 is equal to 1 at node 3, where the value of zeta is equal to 0, and it is equal to 0 at node 1, where zeta is -1, and it is 0 at node 2, where zeta is equal to +1. That means you should have an equation where if you substitute zeta equal to -1 or +1, the N3 should become 0. So that is only possible when we write it in this form, that is C into bracket 1 minus zeta, 1 plus zeta. So either you put zeta equal to +1 or -1, automatically this becomes 0. And the important condition is, again we have to see this, it is equal to 1 at 0, that is 1 minus 0, 1 plus 0, which is equal to C only. So therefore, C is nothing but simple 1. So therefore, our shape function N3 will become 1 minus zeta, 1 plus zeta, or maybe if you want, you can write it as 1 minus zeta square. So these are the three important shape functions for this particular quadratic element. Now let us show on how these shape functions are varying along the length of the element from node 1 to node 3, how exactly they are going to elevate, because the condition is that it should be 1 at the respective value and it should be 0 at all other nodes. So now let me show you, for example, the variation of the shape function. I'll show you. This is our first N1, this is our node 3, this is our N1, and node 1, node 3, node 2, and we know this is equal to zeta equal to minus 1, zeta equal to 0, zeta equal to plus 1, and this is going to be the zeta coordinate as such. And you are already knowing that the value of N1 is always going to be 1 at node 1, and obviously it is going to be 0 at other nodes. To maintain that, I need to pass a quadratic fit such that the shape function varies quadratically and it becomes 0 at node 3 and node 2. So therefore, this variation I can call it as N1 equal to minus zeta into bracket 1 minus zeta upon 2. So this is called the variation of the first shape function, N1, you can say. Similarly, if I want to take the variation of the second, for example, if I take this as my 1, 2 and 3, and again if I take this as our zeta coordinate, and again if I look at this, this is going to be N2, which is going to be 1 at node 2, and it is going to be 0 at other two nodes. So this is the variation of, you can say, zeta is equal to minus 1, zeta is equal to 0, and zeta is equal to plus 1 here. So this represents the variation of the second shape function, N2. You can see always this is a quadratic fit, we call it. This is a quadratic fit, and the value of N2 is going to be 0. And similarly, if I want the third one, see, this is the third shape function is like this, and this is going to be 0. This is 1, 3 and 2, zeta being minus 1, zeta equal to 0, zeta equal to plus 1 here. See here, obviously the N3 is going to be here, this is going to be N3, and the quadratic fit will be like this, and this will be N3, which is equal to 1 minus zeta square. This is what you can write down that, and this is representing the third, you can say, shape function, you can say like this. So in general, if you want to represent these three shape functions, then how to go ahead with the displacement? If I am interested to find out the displacements, how exactly this is going to be found out that? Yes, these are the three shape functions which we have seen. Now, we are very much interested in, say for example, if I have three nodes, see this is going to be, let us say 1, 2 and 3. Now let me say that if this is our zeta, let me say that the displacement of the node 1 is q1 and displacement of node 3 is q3, and this one is going to be q2. So therefore, these are called element nodal displacements. That means if I want to write, I can write it, that is the element nodal displacement vector. If I want to write this, this is going to be q, which is going to be q1, q2 I am writing, not q3. Okay, look at this. This is the very interesting part. Here I am always writing q1, q2, q3. Though the order is q1, q3, q2, but when I am writing in the local coordinate system, I always write it as q1, q2, q3. So therefore, if I want, with the help of these shape function, suppose I am interested in this point, where I want to know the displacement of this point is u. The value of u is depending upon, if it is the value of u at node 1 is q1, the value of u at node 3 is q3, the value of u at node 2 is going to be q2. But if I want in general, for example, from here, let us say this is at a value of some zeta. At zeta equal to minus 1, if you put, that is different. At zeta equal to 0, if you put, that is different. If you put zeta equal to plus 1, you will be getting that. But if I want at any general zeta between minus 1 to plus 1, if I want to substitute, and if I want to find out the nodal displacement, so therefore nodal displacement. Please remember, since it is a 1D element, it is displacement u is given by using the shape functions n1 plus n2 q2 plus n3 Q3. This is the way I can find out. These are called interpolation functions. Once we know the three nodal displacements, the prerequisite is that we should know all the three nodal displacements, Q1, Q2, Q3. In case if we know them, then only we can find out the value of U at any arbitrary point. So this can be written in a vector form. For example, if I change this, it will be N1, N2, N3. And here you can write Q1, Q2, Q3. This can be written in a vector form N into Q. So U is equal to NQ, where N is going to be the three shape functions what I have written here. That is what you can see now. Of course, you can see there what will happen, the value of these things. Now let us say I want to find out the value of this displacement U. Okay, now let us see. What is the at node 1? At node 1, N1 is 1. Okay, and N2 and N3 are zeros. So therefore, if I take our U, it is 1 into Q1 plus 0 into Q2 plus 0 into Q3. So which is nothing but Q1. So therefore, at node 1, the displacement is always equal to Q1. That is what I just now told you. This value of U is going to be equal to U1. Similarly, if you want node 2, tell me what is the node 2? N2 is 1 at node 2 and N1 and N3 are 0 at that point. So therefore, U will become 0 Q1 plus 1 Q2 plus 0 Q3, which is nothing but Q2. Similarly, you will get U equal to Q3 at node 3, because there N3 is equal to 1, whereas N1 and N2 are going to be 0 at these 2 points. So therefore, I can find out this variation can be shown. For example, this variation, if I want to show this on this element, see here, this is the zeta value. If I write this as my node 1, it is Q1, and node 2, if you write it as Q2, then node 1 and node 2. At node 3, I can find out this like this, and this is going to be my Q3. And the general variation is N1 Q1 plus N2 Q2 plus N3 Q3. This is the variation. This is the variation of the displacement. It is not definitely linear. It is parabolic in nature. So therefore, we need to find out the nodal displacement at these 3 points. So what we can find out is the value of U is a quadratic interpolation passing through Q1, Q2 and Q3. This is what you can see from this particular variation of the graph. Okay, now once we know this, now let us move on to the next derivation part of the element stiffness matrix and load vectors and other parameters related to this 1D element. Okay, first let us now start with, see, all of you know, now the strain is given by what, tell me? The strain epsilon is always given by du by dx. As far as the partial differentiation is concerned, it is always du by dx, by, you can say, stress strain relations. But if I use what is called as a chain rule, I can rewrite this as d zeta by dx. This is called chain rule. By using this chain rule, I can find out this particular value. Now, look at this. You already know that zeta is given by 2 times x minus x3 upon x2 minus x1. So, if I take zeta here, it will be 2x or 2 dx. It is upon this part being a constant, I can write it as x2 minus x1. And I have already told you this x2 minus x1 represents the length of the element. Please remember, this is called length of the element. It is across the complete length, x2 minus x1 will give you the length of the element. So therefore, this also you can write it as the dx upon Le. So therefore, if I want d zeta upon dx, then it will be 2 times Le. So if I substitute this in this equation, this thing will become 2 times Le, this will be there, into du by d zeta. This is what you are going to get this. But since you are already knowing that u is nothing but nq, where this is nothing but n1, n2 and n3 into q. This is what we are knowing. So obviously, if I want the du by d zeta, this is going to be d by d zeta of nq. Since q is going to be a constant, this is not going to be affected. So therefore, this can be written as like this: d n1 upon d zeta, d n2 upon d zeta, d n3 upon d zeta. And this will remain as usual. That is q1, q2 and q3 will remain as it is at the outside side legs. Okay. So now let us come to this. What is this d1 by d zeta? See, already you know that n1 is given by minus zeta 1 minus zeta upon 2. You can modify this as minus half into bracket zeta minus zeta square. You can write it like this. So obviously, if I want the dn1 upon d zeta, if I want this, it is going to be minus half 1 minus 2 zeta. So, or you can write it as 1 minus 2 zeta minus upon 2, or you can take it the other way, 2 zeta minus 1 upon 2. This way also you can write it. Similarly, if you go for dn2 upon d zeta, you will get similarly 2 zeta plus 1 upon 2, you get this. Or you can even write it as 1 plus 2 zeta, 1 plus 2 zeta upon 2, you will get this. And in the last way, since t n3 upon d zeta, when you get this, it will straight away come minus 2 zeta. You can see there. Because it is 1 minus zeta square, 1 being constant minus 2 zeta will be the differentiation of that. So therefore, this equation is now getting modified as what? It is modified as dn1, that is 2 zeta minus 1 upon 2, 2 zeta plus 1 upon 2 minus 2 zeta. This will become there, and then this will become q1, q2, q3. Okay. Now let us come back to our original equation of strain. What is strain? See here. Strain is this 2 by Le is already there. That is 2 by, that is strain is 2 by Le into bracket. We get all this. That is 2 zeta minus 1 upon 2, 2 zeta plus 1 upon 2 minus 2 zeta. You will get this, and here you will get q1, q2, q3. This is the entire equation for the strain. Now I can write it in a matrix form. This will be equal to B matrix and this will be Q matrix. So strain is always given by B into Q. This is going to be a general expression for all the elements. Whether you take 1D, 2D, 1D 2 noded bar element, 1D 3 noded bar element, or 4 noded bar element, or even you can take 2D CST element, 4 noded quadrilateral element, or any other higher order element. When you take, the strain expression will become the product of B into Q, where B is called strain displacement matrix. This is called strain displacement matrix. So if you look at this figure, it is going to be 2 by Le, 2 zeta minus 1 upon 2, 2 zeta plus 1 upon 2 minus 2 zeta. So this is called as what is called as strain matrix. This is called as a strain matrix. So once you know the strain, then obviously I can find out the stress. Therefore, stress is always given by Young's modulator into strain, which is E into B into Q. This is going to be the expression for stress in an element. We can find out that. See, a very interesting point. You can compare here and the, you can say one-dimensional two-noded bar element. There you found out that because there my, what you can say, B, strain displacement matrix was a constant. If you look at that, it is because it was a constant. The stress and the strain, they were remaining constant throughout the element. At every node or at any point in the element, the stress was remaining constant. But that is not the case here. If you look at this, here there is a zeta term. That means the strain displacement matrix varies linearly. That means the stress is not constant throughout the element, it varies linearly. If it is 0 here, at somewhere it is 5, exactly after some distance it will be 10, then 15, 20, like that it goes on varying linearly from one end to the other end. So therefore, this stress is linear variation. You can write it here. Stress and strain are having linear variation. This is called what is called as variation of the stress in the linear direction. This is what I just wanted to compare with the one noded bar element and this one. See, once you establish the relation between stress and strain, now let us go to derivation of the element stiffness matrix. See, first let us start with the derivation of the element stiffness matrix. But prior to that, I would like to take an assumption. We will consider some assumptions here. The most important assumption here is the sectional area, cross-sectional area AE remains constant. This is one of the very, very important, this one. And next, the body force, which we represented as F, it is also, that is what rho G, it is also constant. This is what we see this. And the traction, what we find out, traction T is also constant in this case. So that means when you take a particular, you can say, element, and if you consider this as one element, see the traction which is applied on the surface, this is called as the traction. It may be applied on either side, but it is there. And the inside, whatever we show, this represents what is called as body force. That is F equal to mass density into the gravitational constant. This is what we call it, and this is let us say function of x, and this is the length of the element. So if you consider this as one element only, then if you can take like this, the element is always distributed in this manner. This is going to be what we are going to write. It is represented by one single element of quadratic element with a node 1, 2, 3. So with this particular assumption, if we want to write the total potential energy equation, all of you know the total potential energy, which is always represented by pi, is always the sum of strain energy plus what? Work potential. Exactly, it is correct. It is work, strain energy and work potential. So we represent this as U plus V. V of course being negative, and it is due to three forces. V is always due to what? It is due to you can say body force, traction and the point load at a given point. So these three components are involved in the work potential, these two due to that, and this is the strain energy. It is because of stress and strain. This is the amount of energy stored by virtue of the stresses and the strain developed inside the body. So therefore we know already this equation has been already developed in our earlier equation. this if I write for the global equation, I need to use sigma term, and this is going to be E sigma transpose E into A into dx minus, this is the strain energy, half sigma transpose epsilon into dV is going to be, this part is nothing but dV, that is the elemental volume, and we are actually integrating over volume, but when I convert this volume into A into dx, this varies between 0 to L, that is across the length. Then we consider what you call it as body force effect. This is F into A into dx. Of course, it is going to be an integration over the element minus summation integration U transpose T into dx. We are going to take this, and minus summation of Qi Pi. That is it is the product of the corresponding displacement of that node into the point load which is acting at that particular point. That will give you the work potential due to that. See, but there are some interesting things what you know. See, sigma is given by E into epsilon, which is called as E into B into Q, because you know that. And sigma transpose, when you want, this gets interchanged. See, during transpose, these two get interchanged, and strain as such, you know, it is going to be B into Q only. And you also know that dx, when you want to change, it will be Le by 2 d zeta. This is what we have already seen. So if you want to convert this entire equation from X domain to the natural coordinate system, then automatically, you please remember this is integration, what I am talking about. If it is 0 to L, now it will vary from minus n to plus 1. So this is the change when we integrate between the limits from 0 to L to minus 1 to 1. So let us rewrite this equation. So what it will come? It is summation half Q transpose into bracket EE AE LE upon 2, because this Le by 2 has come due to d zeta, minus 1 to plus 1. This is going to be B transpose B into d zeta into the small q will come here, minus summation Q transpose into AE LE by 2 into F minus 1 to plus 1 N transpose into d zeta will come for this, minus summation over E Q transpose AE LE by 2 into T into integration between minus 1 to plus 1 N transpose into d zeta minus summation over entire piece Qi transpose Pi. That is like, it is something like very much similar to P1 Q1. This is nothing but P1 Q1 plus P2 Q2 plus like that. So if there are 3 point loads, so 3 corresponding nodal displacements need to be multiplied, and that is going to be the work potential due to that. See, what we are interestingly find out is, you see here, this part is always representing what is called as element stiffness matrix. Element stiffness matrix. Always remember, from the strain energy equation, always we get, this actually entire part is strain energy. All this part is going to be strain energy, and from the strain energy equation, we always get this. So if I rewrite this entire equation in a simpler form, what I will get is Q transpose, this is if I write sigma over entire E, if I write that, this is Q minus sigma Fe U transpose, this Q transpose Fe minus sigma Q transpose Te minus sigma I Qi Pi. This is what you are going to get this. So this is going to be the total equation where this part is our strain energy. This is the body force vector. It will give you. This is will give you the traction vector. It will give you. And this is giving you the, what you can say, the point loads which are acting at that particular point. So we need to develop the entire equation for what you call it as the element stiffness matrix. So it is going to be, now see here, what is the size of the element stiffness matrix? Because since there are 3 nodes, so obviously the size of the, and 3 degrees of freedom, rather it of course always remember the size of the stiffness matrix depends upon the total number of degrees of freedom. Suppose if you have 3 node with 3 degree of freedom, then the size of the stiffness matrix is going to be 3 by 3 only. But if every node, by chance, if it is having 2 degrees of freedom, then obviously 3 node itself will have 6 degrees of freedom. So obviously, when total number of degrees of freedom are 6, the overall size of the element stiffness matrix will be 6 by 6, not 3 by 3. It doesn't depend upon the number of nodes. The size of the stiffness matrix depends upon the number of total degrees of freedom per element, or even to the structure also when you go, it is again one and the same. That is what you have to see that. So now let us start with how to derive the element stiffness matrix for this 3 noded bar element. Okay, now let us come to the derivation of this. Is one of the very important derivation, element stiffness matrix, which we call it as KE, small ke, we get this. See, looking from that expression, what we find out was, this is given by integration AE LE by 2. This is what we got. Then we got B transpose B into D zeta we got, and this varies from -1 to +1. Okay, so this I just wanted to take it out so that we will come to know now this. So before taking all this, let us keep this afterwards. Let us only take this part. Now tell me, for example, if I want -1 to +1, B transpose into B into D zeta. Let us first do only this much, then we'll add that AE LE by 2 later on to this. See, as you are already knowing, this is going to be, see, it is a 1 by 3 matrix. Now it will become 3 by 1, and this will become 1 by 3. So totally this whole product will be of 3 by 3. So now let us see, what is this B transpose, what I have to write? This is 2 by LE will remain same outside, and you know that this is 2 zeta minus 1 upon 2, 2 zeta plus 1 upon 2 minus 2 zeta. This is the nothing but the B transpose into, we write B, the same thing, that is we will write it as 2 by LE will come, this will come 2 zeta minus 1 by 2, 2 zeta plus 1 by 2 minus 2 zeta into d zeta. This is what is going to come. Now this part I will take it outside. 2 upon LE, 2 upon LE will come 4 upon LE square. So now let us take that outside. So this will now become 4 by LE square into bracket minus 1 2 plus 1. Since I told you this is going to be a 3 by 3 matrix, 1 by 4, when you multiply this into this, what is going to come? 4 zeta square minus 4 zeta plus 1. This will come. Here it will come 1 by 4, 4 zeta square minus 1 will come. Here you will get minus 2 zeta square plus zeta. You will get this. This when multiply these two, you will be getting that. Similarly, here when you come, it is 1 by 4, 4 zeta square minus 1, 1 by 4, 4 zeta square plus 4 zeta plus 1. You will get here. Here you get 2 minus 2 zeta square minus zeta only you will get minus 2 zeta square plus zeta minus 2 zeta square minus zeta. Last one is 4 zeta square, and this is going to be again individual terms need to be integrated between these two limits. So if I change this after the integration, what I will get, tell me? 4 LE square will remain same here. Now this will become what, tell me? 4, 1 by 4 will remain outside. Yes, this will become 4 zeta cube upon 3, 4 zeta square upon 2 plus zeta, this one, first one. So if you go to the second one, 1 by 4 will remain here, and this will become 4 into zeta cube by 3 minus zeta, and this will become minus 2 zeta cube upon 3 minus zeta square upon 2 you will get. And in the next one, what you will get is same, that is 1 by 4, 4 into zeta cube by 3 minus zeta minus 2 zeta cube upon 3 plus zeta square upon 2. See, this is the, after integration, these are the things you are going to get this. Yes, and this is, of course, you need to add between the limits plus 1 to minus 1. So I will just show one of the simple example I will show here. Now let us say if I take 1 by 4 into bracket 4 by 3 zeta cube plus or minus 4 by, or you can call it as 2 zeta square plus zeta between the limits minus 1 to plus 1. So how it will be? This will be 1 minus, here it is 4 by 3 into 1 cube minus 2 into bracket 1 square plus 1 minus, and I say here this is very interesting, this is going to be minus 4 by 3 minus, and minus it will become plus, so this will remain as this, and this will become minus 1. You can see here. So what is the final answer here? You can see here 1 by 4 into bracket 4 by 3 minus 2 and plus 1 is nothing but minus 1. This is there, and here it is minus 3 and this 3 minus 4 minus 9 upon 3, it is like this. I hope you can understand this. This is going to be minus 13 by 3. So here it will come 1 by 4 into bracket 4 minus 3 upon 3 minus plus 13 by 3 it will come. So this is equal to 1 by 4 into bracket 1 by 3 plus 13 by 3, which is equal to 1 by